start the recording. Cool. All right. So, any queries or questions before we get started? So today it's the really the only second part of the trig functions topic. Oh, and I had set it up, or thought I set it up so that you could see your submission marks, but apparently that's not released yet. So they are ready to be released as soon as I can work out how to do it. But yeah, so you should get your submission marks soon. They are there. It's just killing us. It's not by design. You can't see PowerPoint. Can other people not see it? Is it showing for others or not? Cool. The other thing I was going to make an announcement with was, yeah, so the revision quiz is ready for you to practice. The final will be available on Friday and Saturday, because I was a bit late getting it ready for you. And regular submission is due Friday. There shouldn't be too much to do for that one. Do practice the revision quizzes and let me know if you have any major issues with anything that you think it should be correct.
When will you turn the revision quiz on?
Maybe sometime before Friday. I may or may not turn it off at all. The biggest thing is so that you're not getting confused which is the real test and which one's the revision quiz, I believe. So we'll see. If I put it off, it'll be just before Friday, if I remember to do that. It's being stressed about the word quiz. Let me put it this way. I didn't put that much randomization in the quizzes. So even though it is technically a quiz, I really do recommend that you go through the practice ones a few times. So you might see what's required. And for those that do give it a bit of go, let me know if it doesn't seem reasonable to have it in 30 minutes. I think given the given the fact that you can try out the practice one a few times, it should be fairly accessible. Let me put that there. Oh, midterm. Sorry, what was that?
Sorry, what would the alternative be if it wasn't 30 minutes? Would it be more or less?
If you want to tell me you want less time, I can give you less time. If you think it needs more time, I can give you more. Yeah. Yeah. Just do have a go. Let me see how people generally find it. Yeah. Maybe it could be 40 minutes. Maybe. If I switch it, I'll adjust it for anything with time variables. More time, less questions. Pick one or the other. I don't know if I'll give you too much less questions. I'm tempted to change one of them slightly, but I'm hoping that's not going to throw people that have practiced it a fair bit. So yeah. So just wait out for announcements if I decide to do anything drastic with it. But as it stands, it should be what you see on Friday or Saturday. Yeah. Okay. I think that's the only thing to consider for now that I need to call out. Oh, I haven't heard back about the gentleman that has have this completed slides. In fact, actually, now that I think about it, I probably wouldn't have released it before the revision anyway. But yeah, I don't have access to the completed slides directly at the moment, so unless I can get those, I can't really put them up. Doesn't give a range for it. It says bounded by the x-axis, and that should give you a range of values. If it's bounded by the x-axis, then you should be able to find out what the area is taken over. Is midterm exam still being listed at 9? Planning so. Unless there's anything different, whatever it says there goes. Yeah. The midterm exam will still be the 24-hour take-home exam, same as last term. That's the same format. So unless I'm late getting that out to you, it'll be the same date. All right, any other queries, questions? Will we get 3 days like last term? Did you get 3 days last term? Wasn't that from a correction or something? The final exam will be on campus, so it most probably will be. It'll probably be something where we rent out a room and then I'll hand out the paper forms for you physically. I had toyed around with the idea of getting you to do a Maple type one in the labs, but I don't think you want to do that, and I don't think it's easy for me to organize. So yeah, somewhere on campus. So the details aren't finalized yet. So yeah, I'm going to try and see if I can organize that in the coming weeks, but I'm hoping probably around week 11, week 12, maybe week 11 Wednesday, but nothing's really fixed yet. What do you mean should be expensive? Oh, well, it should. We'll see. It might even be here or something. I need to suss that out. So nothing's really yes. It's just saying. Okay. Not finalized yet about the time. I don't think I'll make it more than 2 hours. It might be 1.5 hours, but I'll give you details when all that's in concrete. That's right. In those, it has to be sort of completely as it requires on Mobius. Yeah. So even if it looks very similar, yeah, it does have to be the way I've said that it should be expected as. So I've tried to put the hints in to say exactly what I'm sort of expecting you to put in. Right. Any other queries, questions? I suppose you better get on with the content, right? But yeah, do continue to say something on Moodle forums or email if you want it, just personal. Any further issues? The Moodle forum is probably good for the exam, any quiz issues, because then everyone can kind of see what's expected. Okay, I think we better get on with the lecture, otherwise we'll be talking about this stuff all day. So let's continue on to what we saw last time. Last time we discussed sine, cos, and tan in rate and measure, and the various graphs of sine, cos, and tan. Thanks, Remy. I think everyone can see that, but anyway. So again, a natural sort of thing to continue on from what we can do with sine, cos, and tan is to look at differentiation, integration, look at calculus of these terms. And this sort of hints towards why we care about rate and measure, for one thing. So there is a rule to differentiate these terms, and the first two are sort of, you just have to take it as given, that the derivative of sine x is cos x and the derivative of cos x is minus sine x. And actually this is only true if x is measured in radin, so that's one reason. It's very similar to why we care about the exponential base e, for instance. It's a similar idea. There is a third rule, we can differentiate tan x, that turns out to be sec squared x, and I thought I'll give you a sort of a rundown why that third one holds. But basically you can just remember these three rules. And so one reason why the derivative of tan x is sec squared x is to consider that tan x is sine x on cos x, right? So since we can express it as a fraction, we can apply the quotient rule to find its derivative, given we know the derivatives of sine and cos. So the derivative of tan x is derivative of sine on cos. The quotient rule tells me that it should be this expression, so derivative of sine there and the derivative of cos here. Using the given rules we've just stated, the first two, that's cos x for the derivative of sine minus sine x for the derivative of cos. If we simplify this a little bit, that's cos squared x plus sine squared x on cos squared x. And here's when we use one of our trigonometric identities, is that cos squared x plus sine squared x is 1. So at the end of the day, this is 1 on cos squared x. And maybe it's worth me just mentioning this is equal to 1 over cos x squared, and sec x is 1 on cos x. So this turns out to be sec squared x. This is very similar to your regular submission question on differentiating sec x. So this is actually a bit harder than that one. So this should give you sort of a hint towards approaching that problem. Okay, we're convinced with this rule. Usually you just remember this rule, but you can rework it out. Okay, so that's that one. So let's use in practice. Well, if we know how to differentiate tan, how do we differentiate 3 times tan x? Any thoughts?
Is it 3 times sec squared?
Yeah, so 3 times whatever the derivative of tan x is, and derivative of tan x is sec squared x. Yeah, so it's just simply going to be this expression. Yeah, exactly. What about x squared plus sine x? Well, again, what do we do if it's a sum of terms? We just differentiate term by term, right? So the derivative should simply be 2x from the first term, and then cos x from the second term, exactly. So that's exactly what we'll get here. Okay, so just adding some tools to our arsenal of calculus. Okay, so a natural extension of those rules is if we have a multiple of x, and so you can think either from the chain rule or directly changing the variable that if this is ax instead of x, we simply multiply by the constant at the front. And that's true of all 3 rules. So the only difference here is if this is some multiple of x, then we get a times the sec squared ax. And this is one reason why it matters whether it's in radin or degrees, right? It matters what the units here are. Yes, when x is in radians, this makes sense. So if we want to differentiate sine 3x, what do you think we're going to get?
3 cos 3.
We agree in chat, 3 cos 3x. Is that what we get if we differentiate sine 3x? It's not sine again, so there is going to be 3 at the front, but we need to differentiate the sine term. Yeah, thanks, Jack. Yeah. So exactly, it's going to be 3 cos 3x. Okay. And one more, differentiate tan x on 2. What do we think for the final expression?
Half sec.
Yeah, so half sec squared applied to x on 2. Yeah. Great, I think it was, yep, so everyone's sort of got these things. I wouldn't say times x on 2, Ellen. It's really applied to that. If you wrote it with an asterisk, and if that's sort of how most would read that as sec squared times x on 2, but it's really this applied to x on 2. So there's a difference there. Function applied, not multiplied. Yeah. It's like when you write a function as fx, right? When you write something like this, it doesn't mean f times x. It's not the same thing. Okay, right, so that's using some of those rules. And of course, I mean, we've seen all this with exponential and logs, right? So the next generalization is if we apply sine, cos, and tan to a function, and the chain rule would tell me, well, I just need to multiply by the derivative of the inner function, so f dash x times the derivative of sine, which is cos, applied to fx. So we get this is our rule for the derivative of sine fx. And the same extends on to cos and tan. So the derivative of cos fx is minus sine fx, but multiplied by the derivative of f itself. And you can probably see where this is going. Derivative of tan fx is f dash x times sec squared fx. Okay, so hopefully this just reminds us it's the same process with e and log, just with sine, cos, and tan. So as an example, if we differentiate sine x minus 1, what do you think we'll obtain? Cos x minus 1, excellent. So really we're just taking note that the derivative of x minus 1 is 1. So it's just cos of x minus 1. maybe I would also note here. Yeah, I'll just leave it like that. It's cos x to minus 1. Let's try a couple more of these ones. So if we take a look at cos 2 minus 3x, well, what's the derivative of 2 minus 3x alone? Yeah, as well as got it. So the derivative alone is minus 3 if we differentiate 2 minus 3x. So we multiply that by our minus sign applied to 2 minus 3x. So we'll end up with, here's our minus 3. This is coming from our f dash x. This is our minus sign applied to the term, which is f of our minus sign applied to fx. Okay, I think everyone's getting the idea, right? You concur. It's a bit like that in the doctor's surgery. Hand me a derivative. Stat. Okay, and this becomes 3 times sine 2 minus 3x because those signs cancel out. No, negatives cancel out. Okay, in this one, derivative of sine y equals x plus 10 to x plus 1. Well, we'd go about the same sort of idea. Differentiate the x, gives 1. Differentiate the tan 2x plus 1. Well, we want the derivative of the 2x plus 1 at the front, left with sine squared x. So we should end up with this expression. And of course, we can just write that 2 times x squared x is just 2 times x squared, 2x plus 1. Okay, how come it's a minus 3? Because the derivative of 2 minus 3x is minus 3. There's a minus 3. There's a minus 3 there from that minus. So there's 2 negatives going on. Yeah. Cool. Yeah. Okay. What about tan x squared? What do we think if we differentiate this term? Any thoughts?
2x.
2x, that's from the x squared term, yeah. And then what do we need to multiply that by?
6 squared to the x squared.
Yeah, so 2x times x squared applied to x squared. Excellent, exactly as stated, Ellen. So that's and said by Peter. So we get this expression with our fx being x squared and our f dash x being 2x, right? You don't need to put that in the fx, I just want to clarify that. And that's 2x times x squared, x squared. Okay, and we have another one. Well, what's our technique with this one? If we do want to differentiate x sine x, what would we apply to it? Yeah, so be careful. There's an x, yeah, an x and a sine x there, right? So the method we use is product rule, and here our u is our x, and our v is our sine x. So our u dash is 1, our v dash is cos x, and so cross multiply between these x times cos x plus 1 times sine x. You get this rule exactly. And of course, the 1 just becomes 1 with just becomes sine x there for the first term, and x cos x for the second term. So we should get this expression. Okay, happy so far? Touching on familiar rules and methods. Okay, let's move on. As always, just interrupt if there's something I should go back over. Yeah, can we see what to apply for this one? Differentiating cos x on x. Quotient rule, yep. So u is here, v is here. So if we apply the quotient rule, we'll get v, this is our v term here, u dash, u, v dash there. So the only real new thing is the fact that we're differentiating cos x in our expression. And so that should be minus x sine x on top minus cos x. So this expression, and in fact, actually, yeah, we can take a common negative out the front. So it's minus this entire fraction. Right, okay. Seems reasonable, everybody? Okay, cool. Just thinking if I want to backtrack some of these. Let's try this one. So, again, as you usually would have seen, there's we can. Okay, something's very weird happening here. Anyway, so if we want to look at applications of differentiation, well, typically that's some of the things we've seen. You know, finding equations of tangents or normals, or finding rates of change, things of this nature. So if we want to find the equation of the tangent to y equals tan x at the origin point, well, what do we need to do?
Differentiate it.
Yeah, we need to differentiate it. So differentiate tan x is sec squared x. And well, what's our usual process? To find the equation of the tangent, we need to find the gradient. And the gradient will simply be find y dash 0. So find, that's exactly, so find when x is 0. And I'm just noting here that sec squared x is 1 over cos squared x, right? So we could have put this extra step in, that y dash 0 is 1 over cos squared 0, and cos 0 is 1. So this is 1 overall. So the gradient of our tangent will be 1. And then we know we want to go through the point 0, 0. It's a simple point gradient formula, or gradient point formula, however it's said. So this is the form y minus y0 equals m times x minus x0. So again, this should be something that's familiar once we have the gradient, our m value here. And we substitute the values in. So y minus 0 should be, this is 0, this is 0, this is 1. It should simply be y equals to x. So it's a standard y equals x curve at the tangent. And you might want to compare the graph, right? This is the tan graph. Compare that with y equals x here. It should be exactly the slope. Right. With this one. Okay, just trying to keep track of how many examples we order. Example 12, so we probably have tons of time. Say that. What about this sort of thing? So I want to show that the curve y equals 2x plus sine x is always increasing. So how could we show that? What would be a method to show why it's always increasing? Any thoughts for this one? Its derivative should always be positive. Do we agree in chat? Does that show it's always increasing? Yes, okay, validation. So yes, we'd expect that it always to have a positive gradient derivative, exactly. So that's right. So differentiating this term to check what its derivative is, well, that's 2x plus sine x. Differentiate the 2x gives us 2. Differentiate the sine x gives us cos x. We'll get 2 plus cos x. And is it clear why this is always positive? What's always true about cos x to see why this is always positive? It's always greater than minus 1. Yeah, so it's always between 1 and minus 1. That's true for sine as well. So these are useful inequalities that come out of nowhere. Well, just by properties of the sine graph and the cos graph. So the fact that we can bound cos x is greater or equal to minus 1, which means the biggest, or rather the smallest that the 2 plus cos x term can be is plus 1. Right? So indeed, yeah, so since this is true for all real values of x, this must always be greater or equal to 2 plus or minus 1, which is 1. So the curve is never, it's always strictly greater than 0. It's always increasing. All right, we're happy with that as an application. There's one more before we take a look at integration. This one's slightly more involved one, but not too much. So this one, we want to find the maximum value. What's our go-to approach with these sort of problems? Everyone was happy with the last one, right? Sort of clear there. Okay. Right, finding the maximum values. What's our usual go-to method? Find y dash and y double dash. Yeah, so we want to find where there's stationary points, so we want y dash, and we should classify the stationary points. And in this situation, it's probably easiest to find the second derivative, but not always, right? So let's give it a name, call this function value fx. Differentiate the term to try and find stationary points. So the first derivative is root 3 cos x from the first term there, minus sin x from this, or rather the second term here, and the third term tells me we'll get minus sin x, so we'll get this expression. Differentiate again because we want to classify them, so that's going to give us minus root 3 sin x minus cos x. Sometimes it's worth not doing this until you know you need it. Sometimes it's worth just doing it here, either way. So to find stationary points, well, we want to solve for when this expression is equal to 0. Now you may see this, to those who have their tutorial coming up, you might see this technique in that tutorial, but in this case, the issue is the x is in two different places. So we want to wrap this up into one x variable, so maybe you've seen this technique before. Well, let me ask, what do you think we could do to get x as one term? So we aim to solve for x here. What do we think? Tan x is sin x and cos x. Excellent. So basically, if we divide by cos x, we can re-express as tan x in one term. I think in this scenario, we put this on one side, so we can rearrange it a little bit. You could divide by cos x first. Either way is equivalent. So root 3 cos x is sin x, and if we divide by cos x, we'll get an expression for tan x. So simply divide by cos x. So that's sin x on cos x, which we know is tan x. So tan x is root 3, and this is where we can use our standard rules, our standard triangle, because this will have a standard form. So thinking of this triangle, the half an equilateral triangle, and in rate and measure, this would be pi on 6 and pi on 3 and pi on 6, sorry. Pi on 3, pi on 6. Small angle over 6, bigger angle over 3. And so if we want tan of this, it would simply be root 3 on 1. Or potentially, okay, so that would be the acute angle. So the acute angle would be pi on 3, but if we want this in the region of 0 to 2 pi, we know this is a solution. If we remember our quadrants, it could also be in the third quadrant. So this is also a potential solution, and this is 180 degrees plus this expression, or otherwise it's pi plus this expression. So you could either convert it all to degrees back to radians. In any case, in rate and measure, it should be pi on 3 and 4 pi on 3. Okay, so far we've got candidates with the x values. Happy up to this point, everybody? So solving f dash x is 0 gives us these x values. We also need to classify them and actually find the function values at those points, right? Let me just check if everyone's gone okay. Okay, so given those as our x coordinates, let's proceed to, yep, so that's what we've given so far, pi on 3, 4 pi on 3. Checking for the nature of the stationary points, we can simply check the concavity. hopefully it's not 0. So if we apply the second derivative, well, at pi on 3, this is minus root 3 sine pi on 3 minus cos pi on 3. And reminding ourselves again of our little triangle, here's our pi on 3. If we want sine pi on 3, that's simply going to be root 3 on 2. So this thing should be root 3 on 2, this expression. What about cos pi on 3? What do we think this is equal to? Any suggestions? So adjacent or hypotenuse this time, I'd expect this should be 1 on 2. Yeah. So simply simplifying these expressions, that's root 3 times root 3. So let's just check. Yeah. So this is going to be minus root 3 on 2 minus a half. That's minus 3 on 2 minus a half, which is minus 2. So it should be minus 2 overall. Yeah. And the main point is that's a negative value. So we know we're going concave down, so it should have this sort of shape. So I'd expect this one to be the maximum. Compare that with 4 pi and 3, where we'll do the same process. We're going to get almost the same sort of idea, but this time the sine terms are actually negative. So because this is now in the third quadrant, so the sine term is minus root 3 on 2. The cos term itself is minus a half. So we're just going to get the negative of the negative. So we should expect that this should just be minus 2 or plus 2. If we simplify that. So that should be 2. That's going to be concave up. That's going to give us this minimum point. So out of the choice, well, which one's going to give us the maximum value? The pi on 3 or the 4 pi on 3? Well, that's the concave up one though. That's going to actually going to give us a minimum. Yeah, pi on 3. So going back maybe a couple of steps, that's going to give us a maximum. Okay, so I expect the maximum value is at pi on 3. It's not the actual maximum value itself, but that's what we have to apply to our function to find the maximum value. I feel like I'm going through this a bit fast, but at the same time, they are familiar rules. So using what we know about the derivative properties. Okay, so the last move is just to find that function value, and so we find f of pi on 3. And it's a matter of just simplifying the values out, and I think I did spell this one out a little bit more, so yeah, I actually did explicitly put this in a bit more, so that's root 3 on 2 for this term again. This is a half for this term. So we should end up with 1 plus 3 on 2 plus a half, that becomes 3 at the end of the day. So whatever this function does, its maximum over that interval is 3. All right. Happy? So that does a lot of stuff with differentiability. Next natural question is to talk about integrals. And again, similarly with exponential, let me just check if we're sort of happy with that one. Maybe need a little time to digest it, but it does use the same sort of steps we've seen. Other than the previous slide, could you please write out the line before the greater than or less than? Which one do you mean? The let me go back a bit. Which one did you want to see again? Could you please write out the line before the greater than? Oh, this one again. Okay. As in this explicitly. Yeah. Okay. This is equal to -3 lots of -3 on 2 minus -1/2. Noting here that this works because 4 pi on 3 is pi plus pi on 3. So it should give me the negative of the sign. That's equal to plus 3 on 2 plus 1 on 2. That's equal to 2. Is that sufficient, or? Yeah, I'm keeping in mind that you probably want to see practice a bit of these type of problems in the next tutorial now. So it might be a bit clearer once you've done some of these sine, cos, and tans of radian angles. No worries. Okay, I'm still okay. And this should remind us, is the same sort of rule as the power law, also the same sort of rule as with logs, with constant terms, or with the exponential with constant terms. We can undo the differentiability with integration. We just have to be careful that this only really works with constant terms, and I think I forgot to mention that a should be constant in the slides again. So this comes from the fact that we know the derivative of cos x minus of cos x is sine x. So undoing that, the integral of sine x should be minus cos x. And same sort of thing with cos x, but here we get plus sine x. So just be careful of the ordering, right? So if you differentiate sine, it's cos. If you differentiate sine, cos, you get minus sine. But if you integrate sine, you get minus cos. If you integrate cos, you get plus sine. So just be careful of which one you put the sign on. And then same thing with sec squared. So we know that should give us, that should return us back to tan. And again, you can just usually just memorize these formulas. And yet again, I'm warning you that these are in radians, these arguments. Okay, let's apply our rules. So otherwise it's the standard rules of integration. So if we want to find integral of sine 4x, what do we think? What are we going to get? Straight over minus 1 on 4 cos 4x, excellent. So it's simply this top expression with a equals 4. And again, this is the one that we should get a minus, because if we differentiate cos, we remove the minus again. So you can always differentiate this and see if you get back the same thing. Some other ones. So this is a definite integral. What do you think the first thing is? What's the actual integral of sec squared x? Find tan x between the bounds pi on 4 and pi on. What is our rules about definite integrals? We substitute in one value the upper one, subtract off the substitute value with the other one. So tan pi on 3 minus tan pi on 4. And we use our standard angles, and I might just note that here this should be root 3 for tan pi on 3 and 1 minus 1 for tan pi on 4. Which I think I got wrong in the lecture last time. So it's definitely this term is 1. This term is pi on 3. And I would prefer that you do actually simplify this if you can, if it's a standard angle. So same as if it was a standard degree angle, you should simplify it in practice, because you can't find the exact value. It does, and actually you just have enough. Shall we discuss that rather than an example or not? You do have actually the tools to integrate that now.
What was the question?
Can we find this? Can you find the integral of tan x? what do we think others, do others want to see this, or do we just want to stick with the examples and the slides? I'm a bit hesitant. Sorry?
Examples are good.
Yeah, I think maybe I might leave that for a tutorial. Yeah, just because I want to make sure we do cover the material. But you can do that with what you've given so far. So I'll let you think about that. I think there's 3 or 4 examples. Let me see. I might do 1 or 2 of them next time. Okay, actually, this is a pretty relevant one. I'll let you think about it. Okay, so this example, what do we have? We have the derivative of a function, whatever that curve should be, and the derivative itself is 1 minus 6 sine 3x. And we're given that it passes through the point 0.7. What is the equation of the curve? Any thoughts on what we have to do with this expression, the 1 minus 6 sine 3x? Integrate, right? We want to find what the actual y term is. We want to find a primitive. So a primitive function of this derivative will simply be, well, integrated. So primitive of 1 is x, primitive minus 6 sine 3x is plus 2 cos 3x. So that's coming from the fact that we're dividing the minus 2 there. Minus 3 rather. And so we know that's the equation of the curve. The only thing is, how do we fix the constant? Well, we know it must be the particular one that satisfies going through the point 0.7, i.e. we know that when x is 0, y should be 7. So we substitute those values in. This will give us a fixed value for our c, and that must be our constant value c. So substituting in gets us 7 is 0 plus 2 cos 0. Cos 0 is 1. So c should be 7 minus 2, which is 5. We should have put this extra step in that this is true from the last line. And so our actual function itself should be y is equal to x plus 2 cos 3x plus 5. So again, the constant's important here. And then if we need to find a value from this, to apply to this function, we will just plug in a value of x. Okay, are we happy with this one? Let's take a look at another one. This is probably a good one. So, okay. What are we going to do here? We want to find the exact area under one arch of the curve y cosine x. So effectively just this area. Well, is it pretty simple? What we have to do, the sine graph curve, sine x curve. Exactly, right? Here's our x is 0 part, here's our x is pi part. We simply find the integral of sine x between 0 and pi. So, yeah, crosses those points. We want the area of that integral, definite integral. Integral of sine x is minus cosine x. So it's minus cos x between 0 and pi. Substitute the values in. It should be minus cos of pi. Let me just a bit better. Minus cos of pi minus cos of 0. And cos of 0 is 1, and cos of pi is minus 1. So we should get minus 1 minus minus 1. Look at that. So we should get what's on the screen, which is 1 plus 1, which is 2. Okay, we're happy with that scenario 2. It seems reasonable. This is about at 1, this is about 3.14. So approximately I would expect that's about reasonable as a value. And let me just take a look at, oh, there's 2 more examples. So let me, I think we can get through them. Maybe I might just keep going on for the second example through the recording. So this one we want to consider the curve y equals cos x and the line y equals x. I don't really have the sketch of this, so I'll just sort of manually put it in. But here's one. Pi is about pi on 2 is about 1.7. So it's worth just knowing what this is roughly, since pi would be about here, about 3.14. And so what's cos going to do, it's going to start at 1 and work its way down to 0. So this is the cosine graph, at least in this range. Yeah, not put that part there. And well, y equals x is just a straight line with gradient 1, so that should be directly that value there. So that's 1. So we expect there should be some intersection point there, right? Okay. I guess I should extend this up to pi on 2, but you can see it's just going to go through pi on 2 there. Okay, so we know that there's one intersection point, and so that's what's relevant for the next part. We want to show that the intersection point is at 0.73902, 909. There's not actually a very good analytical way to do this directly, so it's really just from a graph. Yeah, so we basically just want to see where these points intersect, which is when cos x is equal to x itself, and there's not really much of a good way to do that besides sketching it. It's sort of a bit incomparable. So it's really just from the graph. I don't have a very accurate graph, but that's its rough value. And the relevant point here is if you wanted to take a look at this curve, we'd want to find the area bounded by cos x, the line, and the y-axis. So just keep this in place for now. We're after this part, this region here. There's the y-axis, there's the line, there's the curve. We're after this region. So it's one of these ones where we want to integrate between two different functions. So it's the integral of 0 through to a, the approximate value of 0.7, the integral of that value between cos x and x. So to put that information together, this is what we're after. The integral of the upper function cos x minus the lower function x between 0 and a is whatever this approximate value is, this intersection point. Integrate cos x as sine x minus x squared on 2, and between 0 and a. Apply our values between them, so sine a minus a squared on 2 minus sine 0 minus 0 squared on 2. Sine 0 is 0, which is something that we all should know. So this right term is just 0 itself. And at this stage, I would just say it's simple enough to apply the function, apply these values at 0.73909. There are some things you can actually do with this term, but that's probably the most direct way to do this. And so it's going to be whatever this term ends up being as a value, and then it ends up being approximately 0.4005. So that's sort of an approach for that one. Questions with this example? Let me put up the region one more time, because I think that picture says 1,000 words, right? I think that gives us most of the information. Is that we know that whatever this point A is here, we would want the integral between 0 and a of this upper one, the cos x, minus the lower one, which is x, take the integral. And from there we use our usual steps. Right. Do we want to do example 19 now, or leave for next time, or should we skip it? I think this is very similar, actually. Okay, let's try and fish off. I think it's very similar to one of the two problems, actually, so you might re-see it again. So the first thing I want to do, I'll just do it so it's on the recording. Yeah. hopefully I'm not rushing through it too much. So for this sort of thing, cool. So what do we want to do here? We're after the area of this region. So if you have to go, it's fine if you go now. So we want the area bounded by this region, and so the first thing is to consider what are these intersection points. That's going to tell us what our x values are. And so what are we doing? We just want to simply see where the sine x graph equals the cos x graph. So to find those intersection points, we're solving these simultaneously. So both these have to have the same function value, sine x is cos x. Do our same trick, divide by cos x, we can find an equation with tan x. So sine x on cos x is 1, tan x is 1. We know that this is the relevant triangle. So opposite over adjacent, 1 on 1. So we'd want this angle. That's pi on 4 in radian measure. And we can also have this in the third component again. So that's pi on 4. We can also have the third component, which is 5 pi on 4. Very similar to the last example. These are our x coordinates. We should also give the y coordinates because we're asked for intersection points. So we simply substitute these in, and if you substitute it into either sine or cos, say sine pi on 4 is 1 on root 2, back again from the triangle, and if we substitute in 5 pi on 4, that's going to be negative, so negative 1 on root 2. Okay, those are our 2 points. Main point is to find the area is we know the x coordinates. So if we want the area between the two curves, that's going to be the, sorry to go back again in slides, that's going to be the upper one, the sine graph, minus the cosine graph between those x values. So to put that together, that's going to be our integral of this expression between these two bounds. Integrate sine is minus cos, integrate minus cos is minus sine, that's this term. Substitute between these two values, that's going to give us, again, I should spell this out a little bit more, cos 5 pi on 4 minus sine 5 pi on 4 as our first term, minus cos pi on 4 minus sine pi on 4, a few negatives. And this here is going to be minus 1 root 2. This is minus 1 root 2. This is 1 root 2, this is 1 root 2. So there's going to be double negatives. So a positive 2 on root 2 from the top term, and again, still a positive 2 on root 2 from the second term. So at the end of the day, it should just be 2 on root 2. And these are both root 2s themselves. Well, yeah, so there's going to be 2 lots of 2 root 2, which is 4 on root 2, which actually simplifies as 2 times root 2 using some surd rules. So that's going to be the area between those curves. Okay, that's it. I might touch up on this next time as well. Otherwise, next topic is on sequences, I believe. So we start a new topic next week. I'll get some slides up. It's better if you do. It's best. This was one thing I meant to say at the start, so hopefully it's in the recording for people. I'm going to try out some pre-lectures. So because I think some people think it might not be enough time between tutorials and lectures if it's going Monday to Wednesday or Wednesday to Monday. So I might try and put up a very short video that just emphasizes the idea at least. So at least you might be able to try out the questions a little bit earlier, at least after the idea. Yeah, I mean, I don't want to do full pre-recorded lectures because I do prefer the format we have here live. And so that would be a bit much to do the pre-recorded lectures and have full live lectures. It's not really feasible for either of us. So maybe that might be helpful going forward. Okay, sorry that went a bit over again. Well, I think we cleared a few things, especially regarding the assessments this week, which is probably important to address. Okay, thanks everyone. I better let you all to your lecture now, to your tutorial now. Yep, thank you. Again, just let me know if there's any issues. I don't mind it if you post in the Moodle forum if you are trying out the revision quizzes and something looks really strange and doesn't seem to work. I might tweak it. I won't guarantee anything yet. Yeah, just have a go and see how it fares. If I tweak it, I'll make a mention about it. All right, thanks everyone. Is everyone here as well? Cool. Let's stop recording before I say something I should. I think I've already done that. All right, see you Monday, one. Oh, and that's the week 4 flexi week as well. So hopefully that's. Yeah. Thank you. Cheers.